Hello everyone, in this video we will learn about minors and cofactors of a matrix or a determinant. One of the property based on the cofactors of the determinants, and also we will learn about the value of a determinant corresponding to the diagonal matrix or identity matrix. What is a minor? See, if we have a square matrix A of order n into n, where n is greater than equal to 2, it means the matrix is of order either 2 into 2 or more than that. Then any of the determinant which we obtain by deleting one of the row and one of the column of the matrix is known as its minor. It means the order of the minor will be n minus 1 into n minus 1. To understand it more, let's take one of the square matrix A. The elements are represented by Aij. If we want to find out the minor of any element of it which is Aij, minor of element Aij, that is represented by Mij, and that will be a determinant of order n minus 1 into n minus 1 if the order of A is n into n. Deleting the ith row and jth column. For example, suppose we have a matrix A, the elements in which are A, B, C, D, E, F, G, H, J, and the order of this is 3 into 3, and we want to find out the minor of the element that is A12. A12 means first row and second column. It means we want to find out the minor of this element B. That will be represented by M12. So we will leave the first row and the second column. What we are left with? The determinant, that is D, G, F, J. This is the minor of this particular element A12. Suppose we want to find out the minor of A23, that will be represented by M23. To obtain this, we will leave the second row and the third column. See, the element is M23. M23 means second row and third column. This is F. We want to find out the minor of it. Then we will leave this second row and the third column, and we are left with the determinant A, G, B, H. We have left the second row and the third column A, G, B, H. This is the determinant which is the minor for element A23. It means what? The value of the element for which we are finding the minor is not affecting the minor. We have to take the determinant deleting that particular row and the column of that particular element. Just like minor, the cofactor of an element of a square matrix is also to be defined like this. Suppose we have a square matrix A of order n into n, and these elements are represented by Aij. Suppose we want to find out the cofactor of any element Aij of it, then we know what is the minor. Minor is the determinant of order n minus 1 into n minus 1, deleting the ith row and jth column. Here what we will have in the cofactor of Aij, that will be represented by capital Aij, and that is minus 1 whole power I plus j into the value of the minor Ij. For example, suppose we have a matrix A of order 3 into 3. The elements in this are A, B, C, D, E, F, G, H, J. Order is 3 into 3. And we want to find out the cofactor of an element A11. Here I is 1, J is also 1. That will be represented by A11. And this will be minus 1 to the power 1 plus 1 into the value of the minor of A11. The value of minor means we will find the minor by deleting the first row and first column. This will be EHFJ. We know minus 1 power 2, that is square of minus 1 is plus. So this will be plus into the value of this, that is EJ minus FH. This is the way we can find out the cofactor of an element. Let's take one of the numerical example here. Suppose we have a matrix B. The elements in this are 2, 5, 4, 1, 3, 6, 4, 7, 8. And we want to find out the cofactor of A22. That will be represented by A22. Here I is 2, J is also 2, and that element is 3. We want to find out the cofactor of element 3. In that case, we will leave the second row and the second column. And here we will have minus 1 power I plus j, that is 2 plus 2, into the minor of A22. This is 2, 4, 4, 8. 2, 4, 4, 8. Find the value. This is minus 1 power 4 into 2 into 8 minus 4 into 4. This comes as plus, because minus 1 power 4 is positive, plus 1 into 16 minus 16, that is equal to 0. So 0 is the cofactor of this. Just like minor, here also we see that the value of that particular element for which we are finding the cofactor is not affecting the value of the cofactor. Now we can understand the expansion method of a determinant to find its value. See, the value of a determinant is given by the algebraic sum of the product of the elements of any row or any column of it with their corresponding cofactors. Suppose we have a determinant delta, the elements in which are A11, A12, A13, A21, A22, A23, A31, A32 and A33. This is of order 3. To find its value, suppose we want to expand along row 1. Then the value of delta will be A11 into the cofactor of it, that is A11, plus A12 into A12 plus A13 into A13. That is the meaning of this. Suppose we want to expand it along column 1. Expanding along C1. Then the elements of first column will be taken. Delta will be A11 into A11 plus A21 into A21 plus A31 into A31. And that's what we have done. In the previous videos you have learnt how to find out the value. And if you remember, when we were multiplying the minors of the elements of this, we were taking this sign as plus, this minus, this plus, and so on. Why it was taken? See, I have told you that cofactor is having the sign by minus 1 power I plus j. Cofactor Aij is given by minus 1 power I plus j into Mij. Following this, we can remember the signs of all the 9 elements for the cofactors. That is by following this minus 1 power I plus j. We know minus 1, even power of minus 1 is positive plus 1. And the odd power of minus 1 is negative, that is minus 1. It means the signs for cofactors can be remembered like this. If this is the determinant of the matrix, then the signs here will be plus, minus, plus, minus, plus, minus, plus minus plus. Why? Because all the even powers, that is 1 plus 1, this is 1 plus 3, this is 2 plus 2, this is 3 plus 1, and this is 3 plus 3. So this way we can remember all the signs of the cofactors and then find the value of the determinant by expanding it. After learning about the minors and cofactors, we can learn about one more property of determinants that can be said to be the seventh property. And what is that? That is that the algebraic sum of the products of the elements of any row or column of a determinant with the cofactors of the corresponding elements of any other row or column is always 0. That is, suppose we have a determinant delta, the elements in which are a11, a12, a13, etc. Then the product of the elements of first row with the cofactors of the elements of the second row is 0. That is, a11 into the cofactor with a21, that is a21, plus a12 into a22 plus a13 into a23 is 0. Similarly, we multiply the elements of the first column with the cofactors of the elements of the third column. Then also the sum is equal to 0. That is, a11 into a13, a21 into a23 plus a31 into a33. That is 0. Let's understand this with one of the numerical examples. Suppose we have a determinant delta, the elements in which are 2, 5, 3, 1, 4, 6, 2, 3, 1. And we want to find the algebraic sum of the products of the elements of first row with the cofactors of the elements of the second row. That is a11 into a21, a12 into a22, a13 into a23. We know the elements of the first row are 2, 5, 3. So we write here 2 into plus 5 into plus 3 into. Then the sign for the cofactors. We have already learned this is minus, this is plus, this is minus. So we are putting the sign here minus, plus, minus. Now we have to multiply the minus only. The minor for this element will be leaving this row and this column, that is 5, 3, 3, 1 here we are finding. For the second element 4, we are finding leaving this row and this column 2, 2, 3, 1, that is here. Then for the third element we are finding leaving this row and this column 2, 2, 5, 3, that is here. When we calculate the values of these determinants, here it is 5 minus 9, that is minus 4. Here it is 2 minus 6, that is minus 4. Here it is 6 minus 10 minus 4. And simplifying this, we are getting 8 minus 20 plus 12, which is equal to 0. So we know what is a diagonal matrix. Diagonal matrix is in which the diagonal elements are non-zero and all other elements are 0 each. If we have any of the diagonal matrix A, that is A0, 0, 0, B, 0, 0, 0, C. And we want to find out the value of determinant A. That will be A0, 0, 0, B, 0, 0, 0, C. If we expand it about row 1, do we find here A into the cofactor of it, that is B0, 0, C. The second element is 0, third element is also 0, so will it come as A into BC minus 0, that is ABC. It means we can remember this also as a property that the value of the determinant of a diagonal matrix is equal to the product of the diagonal element. The value is equal to the product of the diagonal elements. And using this, if we have a matrix I, that is, you know, identity matrix. Identity matrix. In this we know that all the diagonal elements are 1 each. So can we say that the value of determinant of identity matrix will be equal to 1? So we can remember it directly. We can find out that the value of the determinant of identity matrix is always equal to 1. In the next video, we will learn about adjoint of a matrix, its properties, and to find inverse of a matrix by using adjoint. Thanks for watching my video. If you have any comments or doubts, leave them in the comment box and I will get back to you.